Hello friends. Today's topic of discussion is transmission of random process through LTI filter, that is linear time invariant filter. LTI systems are class of systems used in signals and systems that are both linear and time invariant. Linear systems are systems whose outputs for a linear combination of inputs are the same as a linear combination of individual responses to those inputs. The time invariant systems are systems where the output does not depend on when an input was applied. We'll have a review of linear systems, that is LTI system and convolution over here. Recall that a linear time invariant system consists of two properties, linearity and time invariant. Linearity, if x1 of t tends to y1 of t and x2 of t tends to y2 of t, then we can say that ax1 of t plus bx2 of t is equal to, or that is the same as ay1 of t plus by2 of t. The next property, that is time invariant, if x of t tends to y of t, then we can rewrite this x of t plus tau tends to y of t plus tau. All LTI systems satisfy the convolution property. That is, the output y of t is a convolution of input x of t with a filter h of t. Now we can say that y of t is equal to h of t convolved with x of t. Now, here this star, it denotes the convolution operation defined as h of tau convolved with x of tau. That is nothing but integration minus infinity to infinity h of tau x of t minus tau d tau. For discrete time signals, convolution is defined as h of n convolved with x of n is equal to summation of k is equal to minus infinity to infinity h of k x of n minus k. So this is the review of linear systems, that is LTI systems and convolution. Now here we can see a transmission of random process through a linear time invariant filter, that is LTI filter. We can see here the impulse response we are having here h of t, LTI filter over here. The given input is random process and that is x of t, and the output we are having, that is y of t. The transmission of a process through a LTI filter is given by a convolution integral. Y of t is equal to minus infinity to infinity h of tau 1 x of t minus tau 1 d tau 1. So t1 tau 1 is an integration variable over here. So we are going to transmit a random process x of t through a LTI filter whose impulse response is h of t, and we are going to find out the output, that is y of t. Now here mean of y of t is given as my of t, that is nothing but expected value of y of t. Now we can rewrite this, that is expected value of integration minus infinity to infinity h of tau 1 x of t minus tau 1 d tau 1, where e is a linear operator over here. Now here we can see again minus infinity to infinity integration expected value of h of tau 1 x of t minus tau 1 d tau 1. Now we can rewrite this, that is we can take this separate term, that is h of tau 1, and we can find out expected value of x of t minus tau 1 d tau 1. Now this is nothing but, this the second term, this is nothing but mx of t minus tau 1. So we can now say that my of t is equal to integration minus infinity to infinity h of tau 1 mx t minus tau 1 d tau 1. If x of t is a stationary process, mean mx of t is constant, that is mx. My of t is equal to mx minus integration minus infinity to infinity h of tau 1 d tau 1. Now we can see that my of t is equal to nothing but mx h of 0, whereas h of 0 is a zero frequency response of the system over here. So, from the above equation, we can conclude that mean of the output random processes of LTI system is equal to product of mean of the input random process x of t and DC response of the system. Why it is considered as a DC response of the system? Because we are going to use h of 0, which is a zero frequency response of the system. Autocorrelation function of output random process y of t. Now how to find out this? Now let us Now examine autocorrelation random process of a random process y of t. The autocorrelation function of a output random process y of t, we can write this are y of t minus u, which is expected value of product of y of t and y of u, where t and u are two values of time at which the output process is observed. By using the convolution integral, we found this our y of t minus u is equal to expected value of integration of minus infinity to infinity expected value of h of tau 1 x of t minus tau 1 d tau 1. Similarly, the second term, that is expected value of h of tau 2 x of u minus tau 2 d tau 2. Now, by solving this, we can find our y of t minus u, that is minus integration minus infinity to infinity d tau 1 h of tau 1 minus infinity to infinity integration d tau 2 h of tau 2, then expected value of these two. Here we know that x of t is a stationary random process. So the autocorrelation function of x of t is function of a time difference, the intervals. Now we can put tau is equal to t minus u and we can rewrite this expression. Now we can see a mean square value of a output process r y of 0, that is nothing but expected value of y square of t. Okay, because what it was expected value of product of y of t and y of t minus u, but now it is 0, so we will be getting y of t into y of t. So ultimately we can write this expected value of y square t. It shows that mean square value of the output random process y of t is given by putting tau is equal to 0. So now you can rewrite this expression, expected value of y square of t, that is r y of 0, that is double integration h of tau 1 h of tau 2 r x of tau 2 minus tau 1 d tau 1 d tau 2. That is nothing but a constant. Now we are going to observe a wide sense stationary process and we are going to transmit this process through a LTI system, and then we are going to find out the output of this system. As we have seen, we need to find out h of 0 over here. So in this case, a wide sense stationary random process x of t is given and it is basically applied to the input of the LTI system with impulse response, that is h of tau is equal to 3 e raised to minus 2t u of t. Now here what is asked? It is asked to find out the mean value of the y of t of this system if here it is given that is expected value of x of t, that is nothing but 2. So now by using this we can find out h of 0 and with the help of this again we can find out the expected value of y of t over here, that is nothing but our output. So now let us solve this. We need to find out this h of t here. H of t is nothing but what we are having in the example it is given, that is 3 e raised to minus 2t u of t, and it is given that is expected value is given over here. Expected value what it is given, that is 2. Here we can see e of x of t is equal to 2 over here. So you can write. Now by taking the Fourier transform to find impulse response, we get h of omega over here. H of omega we know that is from the previous equation, that is Fourier transform of h of t integration minus infinity to infinity h of t e raised to minus j omega t over here. Now we can rewrite this. We are having this h of t over here. So that is nothing but 3 e raised to minus 2t u of t. So we can write this and then it can be, this is r h of t and this is the, from the given equation we can write, then e raised to minus j omega t dt over here. Now we can change the integration, that is 3 into 0 to infinity e raised to minus 2t e raised to another term minus j omega t dt. Now we can find out h of omega over here, that is after solving this, that is minus 3 divided by 2 plus j omega e raised to minus infinity minus e raised to 0. So if you find, you will be getting 3 divided by 2 plus j omega. Now this is our h of omega. Now you can find out h of 0 over here. That is nothing but 3 by 2. Now mx of t is already given to us. That is nothing but mx of t or mu of x. That is nothing but expected value of x of t. That is given, that is 2. So if you find out the y of t, here the output of LTI system, h of 0 multiplied with expected value of x of t. So 3 by 2 into 2. What you will be getting here? Y of, if you find out y of t over here, if you find out this, we will be getting 3 by 2 into 2. 2 will get cancelled out. Our answer is 3 now. So here what we have studied the uh, how the x of t random processes pass through LTI system and how to find out how to obtain the output process y of t, that we have seen, and that is by using a frequency response, that is h of omega, and by using h of 0 over here. So expected value of our output process is nothing but mx of t into h of 0, and mx of t is nothing but expected value of x of t. So ultimately we can easily find out the output of a given random process whenever it is passed through an LTI system. Thank you.